Welcome to the quiet engine room of the modern world, a place where geopolitical destiny is measured not in miles of territory, but in nanometers of silicon. If you have ever wondered why a delay in a factory across the ocean can suddenly make it harder to buy a new car, upgrade your phone, or keep a data center humming, the answer usually points back to a single, highly contested island. For decades, the global technology ecosystem has relied on a delicate, highly concentrated supply chain for advanced microelectronics. Today, that supply chain is the focal point of a high-stakes struggle between global superpowers, turning semiconductor fabrication into the ultimate diplomatic and economic chessboard. At the heart of this friction are a few key players. On one side stands Beijing, pushing aggressively for technological self-reliance and domestic industry protection, while asserting its regional vision. On the other side stands Taipei, alongside allied nations like the United States, Japan, and European partners, whose primary stated interests center on supply chain resilience, economic security, and the rigorous defense of intellectual property. Caught between these colliding strategic goals are the multinational hardware manufacturers and fabless chip designers, who rely on an uninterrupted flow of cutting-edge silicon to keep the global economy moving. To understand how we arrived at this fragile juncture, we have to look at the historical evolution of the semiconductor industry. For years, the production of advanced microchips underwent a massive wave of geographic consolidation. While chip design happened all over the world, the actual manufacturing of the smallest, most powerful nodes became heavily concentrated in specific foundries. Chief among them is Taiwan Semiconductor Manufacturing Company, better known as TSMC, which grew to produce the vast majority of the world's most advanced logic chips. This concentration was born of pure economic and technical efficiency. Building a modern fabrication plant, or fab, requires tens of billions of dollars, highly specialized engineering talent, and a precision supply chain that took decades to assemble. However, what started as an efficiency marvel eventually transformed into a profound strategic vulnerability. As advanced microchips became the foundational infrastructure for everything from consumer smartphones and medical equipment to artificial intelligence systems and military hardware, governments began to view this geographic concentration through a national security lens. The realization that a disruption in the Taiwan Strait could instantly paralyze global commerce and industrial stability triggered a seismic shift in policy and legislative measures among major governing bodies. The initial policy shifts began quietly enough, framed as routine trade adjustments and national security reviews, but they quickly escalated into broad legislative campaigns. In the United States, the passage of the CHIPS and Science Act injected tens of billions of dollars into domestic manufacturing subsidies, aiming to bring leading-edge fabrication back onto American soil. Simultaneously, governments across Europe and Asia introduced their own versions of industrial policy, seeking to shore up domestic semiconductor ecosystems, but subsidies were only part of the equation. Policymakers quickly moved from encouraging domestic production to actively restricting the outflow of critical technology. This brought export controls and technological decoupling to the forefront of international relations. Governing bodies began implementing sweeping restrictions on the sale of advanced semiconductor manufacturing equipment such as extreme ultraviolet, or EUV, lithography systems to restrict the technological advancement of rival economic powers. These choke points in wafer fabrication and lithography equipment access became the primary battlegrounds of the new tech Cold War. Access to the machines that print microscopic circuitry on silicon wafers is tightly guarded, governed by multilateral agreements and unilateral trade rules that seek to freeze certain competitors out of the leading-edge race. For Beijing, These export controls are viewed as an artificial barrier designed to stifle economic rise and technological modernization. Stated policies from Beijing emphasize the urgent need for complete technological self-reliance, massive state-backed investments in domestic legacy and mature node production, and the protection of local markets from foreign pressure. The goal is to build an indigenous semiconductor supply chain that is entirely insulated from external sanctions, export bans, and geopolitical coercion. Conversely, Taipei and its allied nations frame their defensive measures around the preservation of economic security and supply chain resilience. From their perspective, export controls and restrictions on technology transfers are necessary safeguards to protect critical intellectual property and maintain a stable international order. They argue that allowing advanced manufacturing capabilities to fall under the control of revisionist powers would create an unacceptable risk of coercion, fundamentally destabilizing global security and economic prosperity. This diplomatic and trade friction has had an immediate and profound commercial impact on multinational hardware manufacturers and semiconductor design firms. Fabless companies, those that design chips but outsource their production, suddenly found themselves navigating a complex maze of compliance requirements, license applications, and supply chain audits. Companies had to rapidly assess whether their products contained restricted technologies, whether their manufacturing partners were compliant with evolving export laws, and how to redesign products to circumvent newly imposed choke points. The traditional model of globalized, frictionless sourcing was replaced by a fragmented landscape where compliance costs soared and supply predictability vanished. To map out how this friction escalated, it is helpful to establish the baseline timeline of events leading up to the current diplomatic standoff. The trajectory began years ago with mounting trade tensions and intellectual property disputes between the world's largest economies. It accelerated when intelligence agencies and defense planners began highlighting the extreme vulnerability of relying on a single geographic node for over 90% of the world's most advanced chips. Matters came to a head when comprehensive export controls were codified into law, placing stringent caps on chip performance, computing power, and tool shipments. What began as a murmured concern over supply chain resilience rapidly hardened into institutionalized technological decoupling, setting the stage for the complex regulatory countermeasures and escalation dynamics that lie ahead. As export controls tightened, major governing bodies introduced a new wave of licensing restrictions and localized production mandates designed to secure domestic technology supply chains. Governments began rolling out tiered authorization frameworks, requiring special permits for the export of advanced lithography equipment, electronic design automation software, and high-performance computing components. Alongside these restrictive licensing mechanisms, industrial policy shifted aggressively toward reshoring and localized manufacturing mandates. Subsidies and tax incentives were deployed on a massive scale to encourage the construction of domestic fabrication plants, often referred to as megafabs, on Allied soil. These mandates required chipmakers to secure a specified percentage of their supply inputs from local or Allied sources, creating a powerful legal incentive to decouple from traditional cross-border manufacturing dependencies. Foundries and fabless firms alike found themselves rewriting their procurement strategies to comply with these dual regulatory pressures, balancing the need for geographic diversification with the immense capital requirements of building localized fabrication capacity. These regulatory shifts triggered a rapid sequence of diplomatic exchanges and trade retaliations between the primary actors. As one governing body introduced stricter caps on advanced node shipments, trade ministries in other jurisdictions responded with countermeasures, including export restrictions on critical raw materials, such as gallium and germanium, which are indispensable for semiconductor production. Diplomatic channels saw heated exchanges over extraterritorial jurisdiction, with regulators attempting to enforce compliance on foreign companies utilizing domestic technology or software in their production lines. Trade delegations engaged in high-stakes negotiations, attempting to carve out exemptions for commercial-grade legacy chips, while simultaneously hardening positions around bleeding-edge architectures. Retaliatory tariffs, targeted entity list additions, and sudden customs audits became standard tools of economic statecraft, creating an unpredictable operational environment where supply routes could be disrupted overnight by administrative fiat. To mitigate these severe supply shocks, foundries and fabless chip designers initiated reported industrial adjustments across their global operations. Foundries accelerated plans to diversify their geographic footprints, breaking ground on new fabrication facilities in alternative jurisdictions to insulate their production lines from regional geopolitical friction. Meanwhile, fabless designers undertook massive engineering overhauls to re-architect their chips. They redesigned products to utilize older, less restricted manufacturing nodes, allowing them to bypass the stringent licensing requirements imposed on advanced architectures. Other firms pursued multi-sourcing strategies, qualifying multiple manufacturing partners for a single design to ensure business continuity if one supply channel became blocked. These adjustments, while necessary for survival, introduced significant engineering overhead, delayed product release timelines, and increased development costs across the entire hardware ecosystem. The ripple effects of this technological decoupling extended deeply into the broader macroeconomic landscape, influencing global inflation and tech sector capital expenditures. The massive influx of capital required to build redundant semiconductor fabrication capacity worldwide translated into higher production costs, which were ultimately passed down to enterprise customers and everyday consumers. Semiconductor capital expenditures soared to historic highs as companies poured billions of dollars into factory construction, equipment procurement, and talent acquisition. This capital-intensive race for supply security coincided with broader inflationary pressures, driving up the price of microelectronics, embedded in everything from automotive systems to cloud data centers. Consequently, technology companies had to reevaluate their investment priorities, shifting funds away from speculative research and development toward supply chain resilience and compliance infrastructure. Compounding these industrial and financial challenges was the intense interplay between the energy grid demands of advanced fabrication plants and regional resource planning. Modern semiconductor manufacturing facilities are extraordinarily resource-intensive, consuming massive quantities of ultra-pure water and continuous electrical power to operate extreme ultraviolet lithography machines around the clock. As governments pushed for domestic fabrication, regional planners had to grapple with the reality that a single advanced megafab could consume as much electricity as a mid-sized city. This created friction between local energy consumers and industrial expansion goals, forcing governments to invest heavily in upgraded electrical grids, renewable energy integration, and dedicated water recycling infrastructure. The expansion of the semiconductor ecosystem thus became inextricably linked to national energy security and environmental sustainability policies, transforming chip manufacturing into a critical test of a region's overall infrastructure capacity. Within this landscape of shifting regulatory frameworks and industrial realignment, several long-term trajectories began to emerge, the first of which involves the possibility of deep decoupling and permanently bifurcated supply chains. Under this scenario, the global microelectronics ecosystem could fracture into two distinct, mutually exclusive technological blocks, each operating with its own standards, equipment supply chains, and software ecosystems. Western allied nations and their industrial partners would maintain a self-contained semiconductor pipeline, while alternative technological blocks would accelerate indigenous research to achieve complete self-sufficiency. This deep bifurcation would eliminate the efficiencies of the globalized manufacturing model, resulting in duplicated research efforts, fragmented software compatibility, and permanently higher hardware costs. While proponents of this scenario argue it guarantees maximum security against supply disruptions, critics warn it could stifle global innovation and create persistent geopolitical friction. Alternatively, a different scenario envisions a future defined by managed technological interdependence and targeted exemptions, rather than total separation. In this framework, the extreme costs and complex interdependencies of the global semiconductor supply chain would force governing bodies to establish negotiated corridors for trade, allowing commerce in commercial-grade and legacy chips to continue under regulated oversight while strictly policing bleeding-edge technologies. Governments might establish bilateral or multilateral agreements that permit allied foundries to share non-critical manufacturing processes and raw materials, creating a more flexible and resilient version of globalization. This managed approach would seek to balance national security imperatives with economic pragmatism, preventing the worst-case inflationary impacts of total decoupling while still maintaining strict guardrails around military-relevant microelectronics. Secondary market players and niche hardware manufacturers have had to adapt to these shifting export frameworks through agile operational strategies and localized pivoting. Companies that build specialized industrial machinery, medical devices, and Internet of Things hardware found themselves forced to audit every component in their bills of materials to ensure compliance with overlapping regulatory regimes. Many of these secondary players established dedicated compliance divisions to monitor real-time changes in export control lists, working closely with legal experts to secure necessary licenses before supply shortages halted their production lines. Some smaller firms also formed regional consortia to pool their purchasing power and share compliance resources, helping them navigate a trade environment that increasingly favored large, well-resourced, multinational conglomerates. Ultimately, the global manufacturing of advanced microelectronics remains governed by a fragile and precarious balance of power. No single nation possesses a completely autonomous supply chain capable of producing bleeding-edge chips from raw silicon to finished package without relying on external inputs, whether in design software, chemical precursors, specialized lithography, or packaging expertise. This high degree of mutual vulnerability has prevented any single actor from enacting a permanent blockade without triggering catastrophic self-inflicted economic damage. Instead, the ecosystem exists in a tense equilibrium of strategic competition, where regulatory levers, diplomatic pressure, and industrial subsidies are continually adjusted to gain tactical advantages without tipping the global economy into open technological warfare. To understand how this dynamic will evolve next, watch for upcoming trade ministry announcements regarding finalized export control thresholds on specialized semiconductor manufacturing equipment and upcoming legislative committee votes on supplementary funding for domestic fab construction.